In this video, I'll try to explain the solution for assignment 1 and try to clarify some concepts that some of you may not be able to understand very well as I see in your assignment. So actually, there are two problems. Let me finish the first one. Problem 1 first. So for the first one, there are 8 particles that form a square is shown, and with distance d between adjacent particle, what is the net potential at point P at the center of the square if we take the electric potential to be 0 at infinity? So actually, the first point we need to consider is that V is actually a scalar. V is a scalar. CA is a scalar, not a vector. The main difference between voltage and electric field is that electric field is a vector. Voltage or electric potential is a scalar. So it is actually a number in the whole space. Every space, the electric potential can be different. It is only a number at a specific point. There are no direction for the electric potential. But for electric field, it's different. Electric field is a vector, so it has x component, y component, or z component if there are 3D problems. So actually, why we need to introduce electric potential V is that V is a scalar, so it is easier to calculate the sum of many voltage or many electric potential. So actually, in this problem, there were 8 particles, 8 charge. So if you just write V equals summation k equals 1, maybe we shouldn't use the k because k is a variable that frequently used in this course, which is 1 over 4 pi epsilon 0. So actually, we may try to use maybe I from 1 to 8. So there are 8 particles, and then we have K, Q1 over R1, Qi over Ri, Qi over Ri. So for the charge 1, we have 1 potential, charge 2, charge 3, 4, 5, 6, 7, and 8. And then we sum all of them together, and then it is done. And actually, in this problem, the number is already designed so that you can find something interesting, something like that. I can show it in the green color. So we have too thick. So we have minus 4q here, and then we have plus 4q here. For these two charges generate the electric potential at point P, it would be something like K times minus 4Q, which is the charge. And then this is R, this is R. And you can simply write it as a square root of 2 times D, but it doesn't really matter. And for the bottom right charge, it generates a electric potential to be K 4Q over R. So it turns out to be 0. So for the two charge sample green color, it will be it generate the overall electric potential to be 0 at point P. And actually, I can use red color, minus Q plus Q. So actually, these two charges also generate the voltage to be 0. And likewise, for this one and this one, minus 5Q plus 5Q, they generate a sum of 0 volt at point P. So the only remaining charges is minus 2Q here. So actually, the answer for this question is nothing but K times minus 2Q over D. This is actually D because this is D. Maybe I can just erase it. V equals. So this is D, this is also D, this is also D. So this is the first one, and the bottom one is same, minus K times minus 2Q over D. So the answer would be minus 4KQ over D. So this is the answer of this question. So this is pretty easy. And okay, so let me explain more about this. So the case is very interesting. It's something like, so suppose here there is nothing, no charge in this plate, in this space. So in this case, E would be 0. And also the voltage would be 0. Okay. So for the second case, we put a charge Q. Too thick. Okay, suppose we have a charge plus Q and another charge negative Q here, and in the middle point we also call it P. Okay, so in this case, in the middle point, V is 0. If it's something like the previous case, V will be 0. But actually, E is not 0. For the left-hand side charge, it will generate a E field pointing to the right side, and also for the right-hand side charge, it will also generate another E field pointing to the right side. So actually, E will be actually K times Q over, this is called R squared. Something like this. Maybe I can write it better. So actually, this will be E equals 2KQ over R squared. So for the third case, so here we have plus Q, also have plus Q, and in the middle point P, and this is R. So in this case, V will be 2KQ over R. And E would be 0. because for the left-hand side charge, it will generate a E field pointing to the right side, and for the right-hand side charge, it will generate a E field pointing to the left side with equal magnitude. So they cancel each other, and then it turns out E will be 0. So this is the main difference when we calculate the electric field and the electric potential. So actually, one more thing I can mention is that in the problem, it mentioned that electric potential to be 0 at infinity. So actually, we know that the equation is something like V equals K times Q over R. And K is a constant, and Q is also a constant when we consider a specific condition. So V is actually a function of R. V is actually a function of R. And in this equation, if we just substitute R equals to infinity, then it will be two constants multiplied together over infinity, which is 0. So it already matched this condition. Is it all right if we assume that the electric potential is non-zero at infinity? The answer is yes. Actually, if we just assume, actually we can just assume, let me move it up a bit. Actually, if we assume that V infinity is 1 volt, it is okay, then the equation can be something like K times Q over R plus 1 plus 1. Plus 1. It would be something like this, plus 1 volt, plus 1 volt. Okay. Which is all right, because why we need to define the electric potential is that it's easy to calculate, and then if we can find the electric potential over the whole space, and then we take the derivative or take the gradient in multi-dimension, then we can find the electric field. So actually, 1 is a constant. So when we take the derivative of a constant, then it will be 0. So it doesn't really matter. It will not change the electric field at any point. It is only a constant, just moving up or down. It's something like consider there's a mass, or if we place it here on the ground or place it higher, then actually the potential of this of here you can define to be 0. So here will be the potential for this one will be mgh, right? So if we define it to be 1, then it will be only plus 1. So it's something like this, It doesn't really matter, because from here to there, the change of potential remains the same. So it doesn't really matter. And something I also need to mention is that which is here. Yeah, the final point I really want to mention is that for this answer, if you already substitute the value of K is actually 8.99 times 10 to 9. If you write it into the answer, So it will be something like 4 times 8.99 times 10 to 9 Q over D. Then it will be something like 3 point something times 10 to 10 Q over D. Then you should write the unit. You should write the unit because in this one, K has its unit, Q has its unit, D has its unit. So you don't need to write the unit for this answer. However, if you already turn it into a number, and here Q still has its SI unit, D still has its SI unit, but this one doesn't has its SI unit. So you need to write the SI unit of the K here, so that it will be legitimately correct. So that's all about the problem one. And let's go to problem two. Problem two is something like this. The electric potential V is drawn in this graph, which is a function of x which is a one-dimensional problem. So in this case, rank the 5 regions according to the magnitude of the x component of the electric field within them. So actually, you need to find the electric field by this, or actually, you need to rank the electric field, the magnitude of the electric field by this figure. And it asks you about the direction of the field along x-axis in region 2 and 4. Why doesn't it ask you about the region 1, 3, and 5? Is because it's 0, so it doesn't really have a direction. So in this question, actually you need to know is that EX should be minus dV over dx. So actually, in one dimension, you can simply write it like this. And actually, when we consider the magnitude, which means that we take the norm or take the absolute value of a component, because magnitude is always non-negative. It can be 0, it can be positive, it can never be negative. So when we consider the magnitude of the x component, it will be something like this. Or it would be equal to this. So we need to consider the slope in this graph in different region. So actually, for region 1, it is a flat line, so Ex will be 0. So Ex is 0 for 1, for 3, for 5. Okay, so this is easy. So so next we need to consider the slope at this region 2 and region 4. And there is no number, so that we can only determine by our own eyes. So actually, Ex at region 2 should be larger than Ex at region 4 and Ex at region 1, 3, 5 are actually the same, which is equal to 0, which is also the minimum possible for a magnitude of a vector. So the answer for part A is like Ex at region 2 larger than Ex at region 4, and region 1, 3, 5 are the same, which is equal to 0. So they are. For part B, okay, so move it up a bit. So for part B, so this is part A. For part B, we only consider part B and part C. We only consider the slope. Actually, the slope at region 2 is larger than 0. Larger than 0. Larger than 0, right? Clearly right. Larger than 0, which means that Ex should be smaller than 0 in this case. Ex is smaller than 0, so it should so it should point to the sorry. So it should point to the negative x-axis. Negative x-axis. So this is the answer of part B. And likewise for part C, the slope at region 4 is smaller than 0. Smaller than 0, which means Ex is larger than 0. Larger than 0. Because we need to consider this one. The slope is actually dv dx. So Ex is minus dv dx. So when the slope is smaller than 0, Ex is larger than 0. And in this case, it should point to the positive x-axis, which is the answer of part C. So one point I want to mention is that many of you write something like minus VE plus VE in part B and part C. In part B and part C, I can't really understand why. Because as I mentioned, voltage is not a vector. Voltage or electric potential is only a scalar. It's a scalar. So voltage shouldn't have this direction. So I cannot imagine what EV plus EV or negative EV means, but many of you have written it in your answer. So I think I really need to explain a bit. So actually, so for this one, it is something like this. And okay, I can explain a little bit more. In the slides, in the lecture slides, I have written something like E vector equals negative V, gradient V. If I write it completely, it will be something like negative partial x in x direction plus partial y in y direction plus partial z in z direction. Ouch. V, something like this, which means that if we, so for gradient, it is something like this in Cartesian coordinate. So if we just explain it, it can be something like plus over partial x in partial v over partial x in I direction minus partial v partial y in j direction, partial v partial z in z direction, something like this. So we use this gradient operator to convert a scalar v into a vector, something like this. But I think you shouldn't write something like E equals to minus gradient V equals you shouldn't write it like this. Because this is a vector, this is a scalar. And so I don't know whether it's a scalar or vector. So if you just assure your math is correct, you can still write it like Ex equals to minus dv dx, but in multi-dimension, it can be write it like this. But you need to care about, oh, this is vector, so this is also vector notation, so that as long as we write equal sign, this equation is actually correct. Okay. So I think that's all about assignment 1, and hopefully you can learn something about that. And if you have any comments, please let me know, and I'll try to explain to you. And see you next time.